All right, so let's start the last session of the day, session number 3. We have 3 papers for this session. We'll start with our first paper by Binglung Wang. He's a first year, well, actually, he's a to-be first year PhD as of October at UCL, and he will be presenting ProteusNeRF, fast lightweight NeRF editing using 3D aware image context.
Yeah, thanks for introduction. Yeah, I'm Binglun. I'll present our work ProteusNeRF, fast lightweight NeRF editing using 3D aware image context. This is a joint work with DAT and Mitra. So in the last 2 years, we could see Radiance fields have repeatedly emerged as one of most popular volumetric representation for casual capture of 3D objects. And thanks for college's work, now Radiance fields can do real-time training and rendering. And due to Radiance fields are easy to use, people hope to use them in industrial application. For example, 5 months ago, a Google DeepMind researcher applied Radiance fields in room view scenario. And also, Luma AI user can create his own 3D assets in Radiance field representation. So here's a question: what's the next step? In applications, one need and challenge is missed is editing Radiance field assets. So in this work, we focus on interactively edit the Radiance field by image editing tool. So let's think about how to edit a Radiance field. A simple idea is we have a Radiance field and we have a rendering view. We can use the image editing tool to edit this view. For example, we can edit it to a fire dragon. Then we can use this edited view to optimize the NeRF. However, it will lead to an issue. It's the other sides edited are missed. So can we edit multi-views? For example, given a Radiance field asset, we can take 3 views and edit them to the fire dragons. But we can see it will lead to inconsistent edited result. If we use these edited views to optimize NeRF, it will lead to the updates NeRF results with inconsistent views. And it also will lead to floaters issue. So our method can solve these challenges. Given a NeRF asset and text prompt or edited views, ProteusNeRF can output edited NeRF asset in 1 minute with 4 KB to 32 MB footprint. Before we introduce our method, let's have a look at related works. To edit a 3D object in NeRF, ClipNeRF edit a scene by optimize global similarity of reconstructed view and text prompt in clip latent space. But this method is limited on editing local objects. To enable local edits, distill feature field first propose to distill 3D features from large scale to the pre-trained model to perform selection. Combine this method with ClipNeRF can achieve local edit, but is still limited on time cost. And Dream Editor distill the NeRF into mesh-based field and then use score distillation to optimize local edit. But this method also limited on editing time. And Recolor NeRF can produce color changes by decomposing a scene into multiple color palettes. But the editing landscape is very limited. Moreover, the color-based selection is not very robust compared to feature-based selection, and it can produce undesired recoloring. To enable a more intuitive interface for editing, the most related work to ours is instruct NeRF to NeRF. it iteratively updates the training set using instructor pixel to pixel and optimize NeRF. In this method, it can preserve consistency, but it limited on editing time cost. In addition, it also limited to local edits. Although existing methods produce good edited results, to maintain multi-view consistency, retraining NeRF remains a computationally expensive problem, and our method can fast handle a variety of edits. So how does ProteusNeRF work? Given a NeRF with our triplane light representation, thanks for previous work, a user can choose a render view with the image patch and indicate the 3D object she wishes to modify. And to keep editing consistency, we propose a novel method, 3D Real Image Context, inspired by work text mesh. In our pipeline, it then renders 3D Real Image Context. For example, here, a 2x2 3D Real Image Context. Then the user can use any image editing tool, either a traditional image editor, for example, Photoshop, or text-guided generative editor, for example, a stable diffusion-based model, to edit the image. And finally, our method can edit NeRF in 1 minute with 4 KB to 32 MB footprint. As for our triplan light model, we use a triplan to represent a NeRF due to its efficiency. As a simplification, we ignore view-dependent effect by eliminating the view direction as an input to NeRF. This is similar to AJ3D work. So for a 3D point, the triplan model will first output its features by interpolation in triplan. Then we use a small MLP to map triplan features to geometric features and density. Then the semantic MLP will map geometric features to semantic features. Finally, the color MLP will map semantic features to color. We also propose a residual MLP to do simple edit. Here, we use a small MLP map semantic features to residual color and add to original color. For edits involving only appearance changes, for example, edit views by hue color mapping in Photoshop. Thanks for our triplan light architecture, we can train a residual edited MLP in 4 seconds with a minimal footprint in 36 KB footprint. And finally, we can achieve desirable edited results. And due to this real-time editing and low memory footprint, we can use the residual edited MLP to achieve layered editing. For example, we have 2 residual MLP. One edited the original NeRF to do color changes, another one to do tone mapping with highlight results. Finally, we can combine these 2 layers to get orange tone mapping flower. As for 3D Real Image Context, as mentioned before, edited rendering views independently will lead to inconsistent issue. To address this challenge, we introduce a simple but very effective solution. We merging multiple images into a single image grid when editing. This allows generative model to share simulated codes when modify the image and output coherence, appearance, and geometry. This solution also can be seen as an approximation to learn an attention map by giving local image context. The most important thing is it's very simple and easy to apply most image editing tool or generative frameworks. Here we show a comparison between iteratively single view updates and iterative 3D or Real image context updates. We could see our methods achieve consistent results without floaters. As for qualitative evaluation, we show a lot of edited sequence, including light changes, appearance changes, and geometric changes. We also compare our method with relative method to recolor in flower acid. We can see the Di5 with clip NeRF editing have unnatural color changes. Although recolor NeRF shows desirable results, its editing framework is less intuitive and limited on complex color changes and time cost. Our method demonstrates precise color changes by image editing tool in 3 seconds with only 4 to 36 KB footprint. We also apply our 3D aware image context with instruct pixel to pixel and the same NeRF-based model of instruct NeRF to NeRF. We could see instruct NeRF to NeRF has artifacts around mouse. When using our 3D aware 2x2 context, it's able to overcome this issue with view consistency. As for quantitative evaluation, we compute clip text image direction similarity during the editing iterations. The blue one is our result. The red one is instruct NeRF to NeRF. So we can see we obtain similar or higher clip score and less editing time and iterations. We also did a user study for ablation experiments. We compare edited iteratively by 3D aware image context and iteratively by single image. We could see most users agree our editing results have more text scene similarity and view consistency. And our methods also have limitations. Firstly, we're limited on geometric changes, and this is a general challenge in NeRF editing. Secondly, our method limited on view-dependent scenario, and it can lead to imperfect 2D and 3D mask, and finally lead to imperfect NeRF edits. To summarize, ProteusNeRF is a fast and lightweight framework for interactive editing of NeRF assets by existing image editing tool or generative frameworks. You can use our method or follow our method to keep consistency by 3D aware image context and build layer editing by residual MLP. Also, our method limited on large geometric changes and view-dependent scenario. You can see more results, paper, details, and code by scanning our QR or visit our webpage, ProteusNeRF.github.io. Thank you.
All right, questions? Maybe I can start with one. So in your geometric editing, you can see it's like with the dinosaurs, you can still, there's like this still tray of the dinosaur like ghostings. Is that coming from something specific, or it's just like lack of views, or?
You mean
no, in the one with the tail, like I think it's in the museum. Like when you remove, you can still kind of see the, if I'm mistaken, on the stairs there.
Oh, which one?
Like
this one.
This one.
Oh yes. I remove the 3D objects by feature selection. So the general idea is it's done by previous work. So when we select the 3D objects, we can set the this 3D mask density to 0, so we can disappear this object. Yeah. So.
Okay.
Yeah, I do have some limitations. Yep.
Hi, very nice results. I have a question about the use of the triplanar representation. So triplanar representation allows you to store those edits and everything much more compactly, and also probably train and get so fast results because of this. Essentially, it's like taking a 3D tensor and projecting it into lower rank, like into those different planes. So through this projection, are you not losing some quality potentially of original NeRF, especially for more concave scenes, not just like spherical like objects, but more complicated scenes? Like, isn't this first step of just projecting into the triplanar representation, are you losing some quality from it, or it just works well in practice?
Yeah, that's a good question. To use triplanar model is indeed to lead to some less quality than some other NeRF representation. But in our experiments, it's only like some very small PSNR comparison difference. So I think it's okay. But it did have a trade-off between quality and time cost. Yeah. Thanks for this question. Yeah.
We still have time for questions. I would have maybe one more question. So the obvious limitations like specular highlights, right? Because those are view dependent, which also limits the scope of materials that you can like use during the editing. Would you have any like insights on how you could extend this to maybe solve this a little bit?
Yes, it's also a good question. Yeah, for the future work, an interesting idea is one for the some stable diffusion model, it should have some work to build lighting direction or lighting views as some embedding. So we can use it to insert it in the NeRF. And in this way, we might use the latent space NeRF. It's a method that output features instead of output color and density. And when it outputs the features, the stable diffusion model will use this feature to output the final results. It's a kind of diffusion rendering. Yeah.
Okay. Thanks. Any more questions? If not, let's thank the speaker again. Okay, our last speaker is not me, but unfortunately he's not here today. So, but he's online. So I'll play his presentation, and then we can ask questions during the Q&A.
I am Zhiying, and I'm glad to present our work, Efficient Visibility Approximation for Game AI using Neural Omnidirectional Distance Fields. This work is a collaborative initiative between Ubisoft LaForge and Ubisoft game production teams. We are trying to solve a real-world practical problem encountered in our game development. To our knowledge, we present the first work to use a neural representation for visibility approximation in game AI and demonstrate a working in-game engine integration. In game development, visibility information is critical for designing complex behaviors for non-playable characters. Here we present 3 examples. NPC perception system requires visibility about the surroundings to make NPC react correctly to the changing environment. Tactical position system requires the NPC to choose the best movement target position that is either visible or occluded from opponents. Line of fire system uses visibility to determine if an NPC should pull the trigger. The standard way for game AI to obtain visibility info is through recasting. Simple form of recast can be expressed as a function that takes a point and the direction as input, then outputs the intersection point of that ray to the scene. The computation relies on array geometry intersections, which is expensive when the scene is complex. Although many techniques have been developed to either speed up recasting itself or to control the range of geometry, the computational cost is still significant in modern games for game AI. We illustrate some situations where the cost can become a bottleneck. For example, when evaluating a large number of candidate movement target positions, developers often perform a limited number of visibility tests as the last verification step. However, if we had cheap visibility information, we could filter out unnecessary positions as early as possible to reduce the overall cost. Another example is the development of stealth pathfinding AI for NPCs, which is known to be a very difficult behavior to develop for NPCs due to the high cost of visibility information. So, it's necessary to develop a more efficient approach. To design our method, we started with below targets. First, the method should run fast on CPU, which is very different requirement than other neural network-based methods today. This is because most game AI applications run on CPU and require low latency response. An inline CPU implementation will be the most convenient way for them to use. Second, the method should not rely on batching. This is because in many cases, the NPC only requests a small number of visibility results rather than a large throughput of tests. If our method runs fast for even single visibility tests, then it can be applied to more use cases. Lastly, the method should be able to scale to the game world without sacrificing the inference speed. From all those targets, you see that we put the inference speed as the highest priority. Our key idea is to replace the traditional recasting with ODF evaluation. In the case of recasting, visibility is computed by comparing two distances. One distance is between the source point P and the intersection point Pi. The other distance is the Euclidean distance between the source point P and the target point P prime. On the other hand, the ODF is a function that takes the source position P and the direction U as input and directly outputs the depth. Thus, the visibility can be computed by comparing the ODF output and the Euclidean distance. We can parameterize the representation by a neural network. We observe that the ODF function is independent of the distance to the target point P prime, so we can partition the game world by grouping the source points. In this way, each local partition with limited number of source positions can be represented by a small neural network, ensuring inference speed regardless the size of the game world. Let's have a look at the related previous works. In the game industry, there are 2D methods tries to reduce the cost of visibility tests. This work is from Naughty Dog and the game The Last of Us. They use 2D height or exposure map to represent the open area and use 2D recast to access cheaper visibility information. The obvious limitation is that it doesn't support 3D environments, such as indoor scenes. Another related area to reduce the cost of collecting visibility info is prop-based methods. These methods require placing probes in the scene and storing spatially arranged visibility information. At runtime, the visibility info can be efficiently computed by interpolating the stored value in related probes. However, there are two main reasons that the probe-based methods are not suitable for game AI applications. First, the probes are mainly designed for rendering tasks, so they are often placed around the camera or a part of the scene. But for game AI applications, the probes need to be placed in a much larger area, which increases the GPU memory cost. Second, the probe-based methods are GPU-based, which is not very convenient for game AI applications to interact with. Another related area is neural fields that represents the scene using implicit functions, which is similar as we do. But standard NeRF and other distance fields required multiple evaluation along array to get the final value. This is prohibitive because we are looking for maximum inference speed. In contrast, our ODF representation only do single evaluation for array. There are efforts that tries to accelerate neural fields. One particular interesting direction is accelerated data structures. Those methods tries to use a small MLP or even no MLP at all, moving most of the parameters to a spatial data structure for faster inference, exchanging memory for faster computation time. The main difference is how to encode directions. In neural radiance fields, the standard way to encode direction is, for example, using spherical harmonics truncated at degree 2. But for our ODF representation, it requires higher frequency details in the direction dimensions. Low degree spherical harmonics is not good enough for our use case. To show this, we try to reconstruct ODF at a single source position. With no encoding, the MLP converges to a smooth function. And here is the results using spherical harmonics with increasing truncated degree for direction encoding. It's clear that to compute visibility, we need higher frequency details, but higher degree spherical harmonics is very expensive. This motivates us to design specific encoding method for directions. We will explain it in a later slide. Let's first have a look at the overview of evaluation process. First, on a source position partition game world, we collect inputs for visibility tests, which contains source point S, target point T. The left side of this figure shows a simple 2D grid partitioned of source positions. Then we input collected information feed into our ODF representation, which includes two encoding methods for position and direction. For position, we use positional encoding, and for direction, we use an accelerated data structure called multi-resolution grid encoding. Eventually, the output distance will be used to compute visibility. The idea of multi-resolution grid encoding is to use multiple 2D grids at different sizes as an accelerated data structure. We first map the depth data on the spherical surface to UV plane, then use nearest neighbor indexing to find the corresponding features on the grid. In the figure, we illustrate a two-level resolution grid from a spherical view and a UV plane view. The feature of a given direction is interpolated from the features stored in 4 nearest pixels. Now let's have a look at the evaluations. To evaluate our method, the key of ODF reconstruction quality and performance is the encoding method in front of MLP. To compare with different baselines in a convenient way, we build an offline environment with 2D grid partitioning the source positions. Next, we collect reference data using request for each source position, and then the data is exported, training and evaluating different representation and encoding methods using PyTorch. Here is the matrix for different encoding methods we tested. We collect 3 kinds of metrics, including classification metrics for prediction performance, parameter number for memory, and the inference time. From all these encoding methods, our method with positional encoding and long latitude projection version have a good trade-off across those 3 kinds of metrics. So we selected this version as the one to implement in the game engine and compare it with recasting. Let's have a look at the in-game evaluation part. The evaluation happens in those 3 scenes. Environment A is a middle-sized scene, contains middle-sized objects and certain proportion of open area. Environment B contains a larger open area with quite a lot of small objects. This scene turns out to be the most challenging one for prediction accuracy, which we'll show in the table after. Environment C is an interior scene. In most cases, the visibility is non-visible between positions. On those 3 scenes, we perform side-by-side execution time comparison with recasting, which is based on Havoc physics. Our method is implemented based on a pure C++ implementation. This recorded video demonstrates how the in-game integration works. First, from the debug window, we select one of the partitions we'd like to test, which is visualized as an orange cube. Inside this cube, the source position is visualized as a blue sphere. Green and red spheres indicates the target position and that our model predicted correctly or incorrectly for visibility result. After model converges, we see there appears more green spheres. Also, because the model inside this partition is learning for all source positions in the partition, so we can check other source positions as well. Here is the quantitative comparison result with recasting. We collect both cold startup and warm startup time because the difference is quite significant for both methods. We found with 128/2 size of MLP, we have a pretty good balance between prediction accuracy and inference speedup. Obviously, recasting inference time is affected by this scene, but our inference time are constant. This is possibly a desired property because it makes the visibility query running time predictable. We also collected memory comparison with recasting. The memory presented here for our method is enabling all partitions in the scene. It is important to note that the flexibility of ODF allows developer to selectively enable disconnected partitions rather than the entire scene to lower the memory cost. Okay. To summarize our work, our major contribution is we present the first method to use learned ODF for efficient visibility approximation for game AI applications. The ODF partitioning is scalable and flexible to scale to the game world. Our main limitation includes, first, our method currently only models the static scenes. Second, our method models depths, so supports direct visibility only. Also, the method is a pre-computational approach, which requires additional offline processing time, for example, collecting data and train the model. Our future work includes feature and encoding improvements, which can potentially improve prediction performance and memory footprint. Another direction of future work is we see the method has a lot of potentials to be extended to other applications, for example, path distance pre-computation, sound propagation, and spatial reasoning. Okay, that's all of the presentation. Thank you for your attention.
Okay, Zaining, I hope, sorry. I hope you can hear us.
Yes.
Okay, great. Thank you. Do you have questions? Yes, we have one in the back.
Hi, cool work and very nice application. So you observe during your presentation, notice that the problem with visibility and those encoding depths, it's that unlike other problems that are encoded in fields, that visibility itself tends to be very discontinuous and sharply changing, and you work around this with your method. However, like, do you take any advantage of the fact that very often we're interested in, for example, probabilistic visibility or probabilistic answers? Like, we want to know, for one example in computer graphics is problem of conservative depth testing, that you want to know for sure if something is occluded, but if it's otherwise, it can be like yes or no, and then you don't really care. So do you think that it's possible to take this insight about the problem of visibility and game AI into account and combine it with your methods? For example, to get some approximate answer early and then maybe do some more costly ray casting or something like this when the answer is unknown?
Yes, I think it's possible because we see our method is kind of one of the underlying piece of information source for approximating visibility. So it can be used for approximating or making some other decisions as well. And we think our method can be one of the information source that can be used for other applications as well.
Maybe a follow-up, because it's your method conservative in this sense, right? Because I think that's the point, right? If you say that you have a wrong prediction, do you know if it's always you miss it because something that was visible is not visible, or it can go both ways? Because for many methods that do like early visibility tests, it's important that it's really conservative.
Yes, so I think one way to do that is you probably can have some confidence boundary or confidence threshold, something like that. For example, you want something that occluded for sure, then you can increase the threshold for the depth testing, so you can have better approximation, better accuracy for that. But the method is not like do the exact, it cannot ensure that 100% accuracy.
There are more questions? I have one question about your partition. Does the size of the partition has some direct influence on the accuracy? So if you reduce a lot the size of the partition, does it also increase your accuracy?
I think the size of partition will for sure affect the prediction accuracies, and it's a kind of trade-off decision between the memory footprint and the accuracy. But from our experiment, that's really depending on the scene and what kind of scene you are applying with. So for the 3 scene we tested, we use 14 meters cube to define our partitions, and it works pretty well in our case. But eventually, when you're designing this, maybe you need to do some experiment on the scene for your use case.
So would an adaptive partition be one way to solve this scene dependence?
Yeah, I think it's a really good direction for using adaptive partitions. And also, just to add it on that, the partition doesn't need to be spatially partitioned, so you can actually group in arbitrary source positions. But we use the spatially partitioned way because we want to compress as much information as possible into the into one model. So spatially, we just make an assumption that spatially partition can make that compression rate maximum. So.
Okay, thank you. Any more questions? If that's not the case, Ziyang, thank you again for being there.
Thank you.
And thank you all the speakers for this session and for the day. This concludes our first day, but not entirely.